section for chapter 8. So we looked at sections 8.1 and 8.2, which comprise the entirety of chapter 8. And rather than move on to a new chapter, I think it's good to do some more problems just to help you all think through how to solve the particular types of problems that you'll see in this chapter and going forward. So I have selected a few problems from both section 8.1 and 8.2 from the back of the book that I thought were generally illustrative of what you'll see. So let's get to it. All right, so we're starting with section 8.1 and problem 7. So here we're saying we have a sample size of 10 from a population that is normally distributed with a population mean of 30 and a population standard deviation of 8. What is the sampling distribution of X bar? All right, so we learned in this section 8.1 that if we are sampling from a population that is already normally distributed, then our sample or our sample mean distribution will also be normally distributed without any sort of limitation as to the sample size. So as long as the population is normally distributed, then no matter how small the sample is, our sample mean distribution will also be normally distributed. So X bar, the solution here is to say that X bar is distributed. Squiggly means distributed normally. And then the important part here is to identify the correct mean and the correct standard deviation for the distribution of X bar. So the mean for the X bar distribution is the same as the population mean, 30. The standard deviation or variance, as this distribution notation usually requires, is different than the population standard deviation. So it's related, but it's still different. So it's the population standard deviation divided by the square root of the sample size. And then this is supposed to be a variance, so I take that and square it. So as long as our population is normally distributed, then so is the X bar distribution, and it has a mean of 30 and a variance of 8 over square root of 10 squared, or a standard deviation of 8 over square root of 10. Okay. All right, now we're looking at problem 15. In problem 15, we are given a sample of size 49 from a population whose mean is 80 and standard deviation is 14. So this is a multi-part problem. First part, part A asks, how is X bar distributed? Okay, so here we have not been told that the population is distributed normally. So we cannot immediately assume that the X bar distribution is normal as well. However, since the sample size exceeds 30, we can assume that the X bar distribution is normal, even though we don't know the distribution of the population. So the answer is, since 49 is greater than 30, means X bar is normally distributed with a mean of 80 and a variance of 14 over the square root of 49, which is 7, right? I'll just write it out. You can simplify this, and that would be squared for variance. Okay, let me just zoom in on that. Try at least. Hold on. There we go. So we can simplify this here, right? This would be 14 divided by 7, which is 2. 2 squared is 4. So this would be normally distributed with a mean of 80 and a variance of 4, or a standard deviation of 2. So that all hinges on the fact that the sample size exceeds 30, since we do not know how the population is distributed. That was not given. Okay, so now that we know that the X-bar distribution is normal, we can compute probabilities. So the first probability they want us to compute is the probability that X-bar is greater than 83. So I've shown you how to do this a couple times. Here we'll do it with the calculator. To compute these probabilities, we're going to go to second, then vars, then choose the Normalcdf function, which is the second option. And then here we want to give it a lower bound, an upper bound, a mean, and a standard deviation, all in that order. So lower bound is 83. Upper bound is something very large. So infinity, I do E10. The mean we just determined was 80. And the standard deviation, when we simplified it, was 2. So I'm just putting in the simplified standard deviation there. So we put in all of that info, and boom, it spits out a probability 0.066. Okay. So for each one of these problems, we're just going to be using the Normalcdf function to compute the probabilities. So now we want to compute the probability that X-bar is less than or equal to 75.8. It's worth mentioning here, in case it causes any confusion going forward, that for continuous random variables like X-bar, less than, or when we're computing these probabilities, there is no fundamental or numerical difference between computing the probability that X-bar is less than or equal to 75.8 versus X-bar is strictly less than 75.8. They're actually identical. The numbers there would be no difference in the computation. So don't let that trip you up. It doesn't matter whether it's less than or equal to or less than. All right. So again, X-bar is normally distributed, so we can use our Normalcdf function. We want to give it a lower bound, an upper bound, and a mean and a standard deviation. Since this is a less than or equal to, the lower bound will be negative E10, something very, very small, negative 10,000, negative 1 million, something. Upper bound will be 75.8. Mean was 80. And standard deviation was 2. So that's 0.01718, 0.018. All right, and finally, we want to find the last probability. Trying to squeeze this all in on one screen. Hold on. Okay, so yet again, we know the X-bar is normally distributed, so we can use the Normalcdf function to compute this probability. Here, the lower bound is 78.3, upper bound is 85.1, mean is 80, standard deviation is 2. Hopefully this is starting to get easy, routine. So our result, the probability of our random variable X-bar being between 78.3 and 85.1 is 0.797. All right. And so that's how we compute these probabilities. Now, something that I haven't been doing as I work these problems out, which can be helpful when you're first getting started, especially if you are having trouble identifying lower bounds and upper bounds and all of that stuff, is to maybe think about this graphically. So let me just give you a little guide. so you don't have to think too hard, because I know people don't like to think very hard. It's uncomfortable. So here's a general guide for this. We have basically three distinct possibilities. First possibility is let me just say this. We're going to say X, the random variable X, is normally distributed with a mean of mu and a variance sigma squared. So three possibilities. We can first compute the probability that the random variable X is less than some value. I'm going to call it alpha. Okay. So we want to compute this probability. So I'll do two things for you. First, I'll show you what it would be in the normal CDF function. Can I zoom out? No. Okay. So normal CDF function, you'd have an upper bound, lower bound, or lower bound, upper bound mean standard deviation. Here, because it's less than or equal to, the lower bound is negative infinity. So I do the negative E10. Upper bound will be alpha, then mean, then standard deviation. Pictorially, you have your bell curve. You are looking at alpha is somewhere. We don't know where alpha is. There is no numbers. It could be to the right or left of mu, which you know is in the middle. I'll put it to the left. So we are computing the area of the shaded region as seen there. So this is the first possibility. Second possibility, probability that our random variable is greater than or equal to alpha. In terms of the normal CDF function, this is going to be lower bound alpha, upper bound something very large, E10, and then mu sigma. In terms of a picture, we've got our bell curve, we've got our mu. Alpha could just be in the same place. And so we're computing the area of the shaded region. Here. And the third possibility is we're looking at the probability that our random variable is between two values. In which case, in terms of the normal CDF function, that's alpha, beta, mu, sigma. Look at all those Greek letters. All right, and pictorially, bell curve, mu. Again, I'm just putting alpha and beta in some random place. They could be anywhere, but as long as alpha is less than beta. And so here we are computing the area of the shaded region between alpha and beta. So you can see these are really the three distinct possibilities. As long as you can boil the problem down to one of these possibilities, you know exactly how to input it into the calculator to get the answer, and you can see what pictorially you are computing. So this is a useful thing to have in your notes and to reference as you're working through these problems. Okay. Moving on. We're going to do one more problem from 8.1. All right, so here we are looking at a application problem. So we're told the time required to get an oil change at a 10-minute oil change facility is skewed right. So what they mean by telling us that the distribution of oil change times is skewed right is they're telling us that the oil change time is not normally distributed because it's skewed right. That means it's not symmetrical. And we know that if something's normally distributed, it must be symmetric. So we're starting with a population that is not normally distributed. That's what they're telling us. they tell us that then the records indicate that the mean time for oil changes is 11.4 minutes with a standard deviation of 3.2 minutes. So records indicate that this is the mean and standard deviation. So these correspond to a population mean and a population standard deviation. So everything here has told us that the population is not normally distributed, and it has a population mean of 11.4 and a population standard deviation of 3.2. Okay, so first question is, what does the sample size need to be in order to assume normality for the X-bar distribution? Okay, well, we learned this from the basically from the central limit theorem. We need if we're starting with a population that is not normally distributed, then we need a sufficiently large sample in order to guarantee enough normality for the sample mean distribution. So we were told that N should be greater than or equal to 30. So that's a fixed result. All right. Second problem, we're start with a sample that's equal to, with a sample size of 40. We want to know what is the probability that our X bar is less than 10. Okay, so by telling us that the sample size is 40, they're telling us that we are in excess of 30. So that means we can assume normality for X bar. So 40 exceeds 30 implies X bar is normally distributed, and it will have a mean of 11.4 and a standard deviation or a variance of 3.2 divided by the square root of the sample size, which is 40, and the variance we square. All right, so that's the first piece of the puzzle. Now we want to compute the probability that X bar is less than 10. So just as I showed you, this is a Normalcdf function problem. Lower bound is negative E10, something sufficiently negatively large. Upper bound is 10, mean is 11.4, and standard deviation is 3.2 divided by the square root of 40. So we're going to punch that into the calculator and get an answer. Second vars, second option. Give it all the inputs as indicated. 10, a mean of 11.4, and a standard deviation of 3.2 divided by the square root of 40. Close parentheses. Enter. Something went wrong. Uh-oh. Let's see. What did oh, I see. I see the problem. I put a comma here instead of an E. There we go. All right, so we get an answer of 0.0028. So let's just call it 0.003. So that's pretty small. So consider what that means. That means that for a 10-minute oil change facility, the likelihood that you're going to get an oil change in less than 10 minutes is 0.3%. Very low likelihood that you'll get in and out of a 10-minute oil change facility in less than 10 minutes. Okay. Now, please excuse the scribbling here. I tried to write this down and messed up. So part C, we're saying we have a sample size of 40. Then the question is, for what upper bound would the probability that X bar is less than that upper bound would be less than or equal to 0.10? Okay, I know that's kind of a hard thing to write. It's almost easier to just draw a picture. Now, what we know is that X bar is normally distributed. We have a mean of 11.4, and we're being asked for what upper bound, so M is what I called it, for what value M is the area to the left of M the probability of X bar being less than or equal to M less than or equal to 0.10. So we're trying to find this M value. Okay, so we learned how to do this actually back in the in chapter 7 when we were talking about the normal probability distribution. So this is actually an inverse norm problem. So M is equal to the inverse norm. And here again, with inverse norm, you need I'm pretty sure if I remember correctly, and a lower bound, an upper bound, I mean, and standard deviation as well. No. Sorry. No, you just need an upper bound. So the inverse norm only works this way. So if they were asking for a lower bound instead of an upper bound here, then we'd have to do some trickery. But since they're asking for an upper bound, that's exactly what the inverse norm function does. So so the inverse norm takes in an area, I mean a standard deviation. So the area here that we're interested in is less than or equal to 0.10. So that's the area. Then the mean is 11.4, and the standard deviation is 3.2 divided by the square root of 40. So that's all the inputs for the inverse norm function. We get to it by second vars again, go down, it's the third option, inverse norm. First input is the area or the probability, then the mean, then the standard deviation. And so we get a value of 10.75. So as long as, so what they're saying is that here, this result is saying that 10% of random samples with a size of 40 will have a sample mean equal to 10.75, or 10% of the time, 10% of customers get an oil change in 10.75 minutes. So that's what that means. Plugging in my phone. Okay, so that's some exercises from section 8.1. Now we're going to look at 8.2. Okay, 8.2, we're using a lot of the same sort of ideas that we did in 8.1 when we're talking about the X bar sampling distribution. But now we're looking at the sampling distribution for the proportion, the sample proportion. So recall the setup. You are doing a survey of a population, of a sample that's drawn from a population. And in this survey, you are asking basically a yes or no question. Did you or do you not possess this quality? And we're interested in the proportion of individuals within the sample that possess the quality that we're interested in, right? So this is just like this. Basically, this is the continuous version of the binomial probability distribution. It behaves very much like a binomial because we're only interested in two possible outcomes, either possessing the quality or not possessing the quality. All right. So first problem is problem 11. Here we're told we have a sample size of 75 that's drawn from a population of size 10,000, and whatever the particular quality that we're interested in, there's 0.8, a proportion of 0.8 or 80% of the population has this quality. All right. So the first thing we want to do is describe the distribution of p hat, which is the sampling proportion. So remember how this works. We need to first determine whether or not the p hat estimator is normally distributed. And we do that by looking at n times p times 1 minus p and asking, is it greater than or equal to 10? So for us, this is going to be 75 times 0.8 times 0.2. So we punch that into the calculator, 75 times 0.8 times 0.2, and that gives us 12, which is definitely greater than 10. So that implies that p hat is normally distributed. How is it normally distributed? It has a mean of 0.8 and a variance equal to the square root of 0.8 times 0.2 divided by 75, and then all of that squared for variance. Zooming in on that. So once we know that n times p times 1 minus p is greater than or equal to 10, then we can assume that p hat is normally distributed. Its mean is the same as the population proportion, and its variance is given by this expression. Square root of p times 1 minus p over n, and then we square that for variance. But this, what's inside the square here is your standard deviation. So that's why I always write it with the square. All right. So yet again, just like with the X-bar distribution, once we know, sorry, I'm trying to get this right. Once we know that we're dealing with a random variable like p hat that is normally distributed, then we can calculate probabilities. So this is just like what we've been doing. We want to calculate this probability. We're going to use the Normalcdf function. Here we have a lower bound of 0.84, an upper bound of something sufficiently large, a mean of 0.8, and a standard deviation that is equal to 0.8 times 0.2 over 75, all square rooted. So that's what we need to punch into the calculator to get an answer for this probability. Second vars, Normalcdf. 0.84 is our lower bound, something sufficiently large for our upper bound, a mean of 0.8, and a standard deviation equal to the square root of 0.8 times 0.2 divided by 75. And we get a probability of 0.193. So the answer here is 0.193. Okay, and so we can just keep chugging along. They want us to compute another probability. We know that this is going to be a normal CDF again. Now we have a lower bound of something sufficiently negative, negative E10, an upper bound of 0.68, a mean of 0.8, and a standard deviation of 0.8 times 0.2 divided by 75, all square rooted. So before I proceed, one reason I always write the standard deviation this way rather than compute it and then just write the number over and over again is, one, I continue to emphasize how you compute the standard deviation. So every time I write this, you're seeing the formula, you're using the formula. The second reason is that when I punch it in the calculator, if I punch it in using this form, then I don't make any rounding errors. I'm giving it the entire number as opposed to rounding the number for the standard deviation and then inputting it. inputting it. So it gives me a more accurate result in the end of the day. So I just hit second enter and it brings back up the previous result. And now I just need to change out the inputs. So negative E, and then something sufficiently large, negative E10. And then our upper bound was 0.68. And all the other parameters are the same, a mean of 0.8 and a standard deviation of that. Punch it in and we get a very small result of 0.0047, we'll say. So computing these probabilities, not really any different than doing it for the X-bar distribution. The only thing that changes in these cases, in this case, is what is the mean and what is the standard deviation for the distribution. So you know it's normally distributed, but the mean and the standard deviation, depending on whether it's an X-bar problem or a p-hat problem, changes. So that's the only tweak. All right. So last problem for the problem session, number 24 from the back of the book for 8.2. Here we're told that a sample of 100 teenagers are asked if they ever took meds for ADHD. Okay, so we're going to consider a success in this case, or the quality that we're interested in is the answer, no, I did not take meds. Okay, so it's not taking meds that is considered the P in this case. Okay, now the question is, in order for the p-hat distribution to be normal, how many more teenagers need to be sampled if we want, I should say, right. So how many more teenagers do we need to ask in order for the p-hat distribution to be normal if part A, we assume that the population proportion is 0.90. So we know that in order for us to assume normality for p-hat, we need n times p times 1 minus p to be greater than or equal to 10. So we don't know what n needs to be. We know that p is 0.90 and 1 minus p is 0.1. This needs to be greater than or equal to 10. So if I rearrange this, then I see that n must be greater than or equal to 10 divided by 0.9 by times 0.1. So we punch that into the calculator. I'm gonna scooch this up. So n needs to be greater than or equal to 10 divided by, and here's important, put down parentheses, 0.9 times 0.1 in parentheses. So greater than or equal to 111.11. So we can just say that rounds up to 112 because we need to have a whole number of people. So we round it up to 112. So the question is, how many more? So we started with sampling 100. We need to sample 112 in order to assume normality. So the answer is that we need to ask 12 more. All right. So for part B, we're doing the same thing all over again, except now the population proportion is changing. So we need, if I wrote down a general equation, in order to have normality, we need the n, the sample size needs to be greater than or equal to 10 divided by p times 1 minus p, which for us is 10 divided by 0.95 times 0.05. So that is equal to 10 divided by, put down parentheses, 0.95 times 0.05. And that tells us that the sample size needs to be 211. We round up. And so we already sampled 100. We need 211. So we need 111 more. There we go, 111 more. So you can see how to do these problems when they're asking about sample size for proportions. This is the inequality that needs to be satisfied. The sample size needs to be greater than or equal to 10 divided by p times 1 minus p. Okay, so that concludes the problem session for 8.1 and 8.2. Keep your eyes peeled. There'll be homework and a quiz.